Hello, everyone, and welcome back. Over the previous few videos, we've been talking about Riemann integration, and in particular, how we can define the Riemann integral as a limit of Riemann sums. Now, what we saw in the previous video is that there's an alternative criterion for determining if a function has a Riemann integral, and that is Darboux's criterion. Now, what Darboux allows us to do is move away from evaluation points. Remember, the original definition of a Riemann sum says that you have to be able to take that limit independently of your choice of evaluation points. Now, what Darboux allows us to do is just take the maximum and minimums on each of these little subintervals and ask ourselves if these upper and lower sums converge together into the same value. Now, what we're going to do in this lecture is look at some consequences of Darboux's criterion. So some results that we can get using this alternative, maybe even slightly simpler characterization of Riemann integrable functions. And in particular, what we're going to see is that continuous functions are themselves Riemann integrable. Of course, this is what we should expect, right? But what we're also going to see is that monotone functions are Riemann integrable. And what this means, as we'll see through an example, is that there are functions that are not continuous but are Riemann integrable. So this tells us that that infinite dimensional space of continuous functions sits inside of a much larger class of Riemann integrable functions. So in terms of vector spaces, this says that C of AB is contained properly inside of R of AB, the space of Riemann integrable functions. And what we'll close with is an alternative criterion due to Darboux. So if you remember, Darboux's criterion says that we have to be able to take that limit in terms of meshes getting smaller and smaller and smaller for all possible partitions of the interval, similar to what we saw with the Riemann integral. Well, what we're going to see with this alternative criterion is that as long as you can find a single mesh that makes things appropriately small, then we can still infer that we have Riemann integrability. Now, this is more in line what you probably saw in a calculus class, because you're using, say, left Riemann sums or right Riemann sums or some very, very simple rule in order to converge yourself into that Riemann integral. Okay, so we're going to get there, but let's start with a theorem that tells us that continuous functions are themselves going to be Riemann integrable. So this will be the first theorem of the day, the first major result. And this says the space C of AB is contained in R of AB. And what this actually means, so that is every continuous function on a closed finite interval, so on AB, is Riemann integrable on AB. So again, this should make sense. This should be fairly easy to intuit, because this is a desirable quality. Remember, we really care about continuous functions. These are the functions that we are most interested in, particularly in this class. And so if we weren't able to integrate all continuous functions, then we might have to rethink our definition of the integral. Okay, so let's take a look at the proof. The proof is going to use Darboux's criterion. So what we want to do is we want to say if we pick a random element, an arbitrary continuous function, we want to show that this thing is itself Riemann integrable. So let's say let f be a continuous function on AB. Okay, now, since we have a finite interval, a to b, we also know that f is uniformly continuous. So also, we know f is uniformly continuous on AB, right? We proved this back when we were talking about continuous functions. So not only is this thing continuous on the interval, it's uniformly continuous on the interval. Now we want to use Darboux's criterion. So that means we need epsilon greater than 0, right? We want to show the upper sum minus the lower sum is smaller than epsilon when we have an appropriate partition. That's what that limit tells us from Darboux criterion. Then we know there exists some delta greater than 0 by the uniform continuity of our function f. So such that if I take 2 points in the domain that are within delta of each other, this implies that their images under f are within some appropriately small value of each other. And I say appropriately small because I get to choose what it is as long as it's not positive. So I'm going to choose epsilon over b minus a, the length of the interval. And this works for all x1 and x2 in my domain. That's what the uniform continuity says, right? Remember, continuity is focused around a single point. Uniform continuity over the entire domain. Doesn't matter where you focus yourself. This is always going to be true. So as long as I look at 2 points close enough to each other, then we're good. Okay, then for Darboux criterion, we need a partition. So now let P equal to a partition of my domain, let's say up to xn, such that the mesh is smaller than delta. And this is the same delta that I got from uniform continuity. So then in each subinterval, so each subinterval xi to xi minus 1 to xi, since any point that is chosen inside this interval is within delta of any other point in that interval, right? That's what the mesh tells us. The mesh says that this is less than delta. So each subinterval has length less than delta. Well, that tells us that their images are less than epsilon over b minus a. And in particular, we have that the supremum, the maximal value on there, minus the infimum, the minimal value on there, is less than epsilon over b minus a. That is just using the uniform continuity argument. And this is since mi and little mi are actual values of f by the extreme value theorem. So EVT, extreme value theorem. Remember, the extreme value theorem says that a continuous function on a closed interval achieves its maximum and minimum values, its sup and its inf. So since I'm restricting to a closed subinterval, xi minus 1 to xi, that tells me that the max and the min are achieved on this thing, and therefore I actually have this inequality from uniform continuity here. Okay, now what does this mean? This tells me that if I look at the upper sum minus the lower sum here, well, these are just Riemann sums using the maximal and minimal values. So let's plug everything in. This is going to be capital Mi minus little mi times delta xi, which I know that I've got this capital Mi minus little mi, that's less than epsilon over b minus a times delta xi. Now, epsilon over b minus a, that is a constant. We know what happens when we sum up all of the xi's. You just get b minus a. And so this thing is within epsilon. The upper sum minus the lower sum is within epsilon of each other. And so hence, this tells us that the limit as the mesh goes to 0 of the upper sum minus the lower sum is equal to 0, which tells us that f is Riemann integrable by Darboux criterion, right? So remember, we're using Darboux criterion. That's where the upper and lower sums come from. And we showed that this limit goes to 0. So that's a nice result, right? That tells us that all continuous functions have a Riemann integral. That's a very, very important result here. Now, let me give you another characterization, right? So we want to be able to say, what functions reside in this space? Remember, we proved that the space of continuous functions is infinite dimensional. It's enormous. that tells us that the space of Riemann integrable functions is also enormous, right? Because it has every one of those infinite dimensions from the continuous functions, but the next theorem is going to show us that you actually have way more. So let me give you another result here. Again, we're going to use Darboux's criterion to prove this. We're going to say if f is monotone on AB. So it could be increasing or decreasing. That's what monotone means. Then f is a Riemann integrable function. Okay, so how are we going to prove this? Well, this one is actually easier to prove than the previous example, and it just comes from those monotonicity properties. So let's start by supposing f is increasing. So suppose f is an increasing function. Remember, monotone means increasing or decreasing. Okay. Then for each partition, P of AB, we have, well, let's take a look here. The upper sum minus the lower sum. Again, just using what we had from the previous proof. So I'm just going to write this in and then we can talk about it. It's the sup minus the inf. But this thing is monotone. So it means that its maximal value is at the rightmost of each subinterval, and its minimal value is at the leftmost of each subinterval. So what does this tell us? Well, first of all, each of those delta xi's is less than or equal to the mesh, right? The mesh is just the maximal value of delta xi's. And then capital M of I for each subinterval is the right endpoint evaluated at f, right? Because this thing is increasing across the interval. So the biggest possible value is at the right, and the smallest possible value is at the left. But now we have a telescoping sum, right? As we're adding and subtracting the middle points, the only ones that we're left with are the endpoints. In particular, we're left with f of b minus f of a, because everything else in the middle there gets added or subtracted. Added and subtracted, I'm sorry, because this is a telescoping sum, leaving us with just f of b minus f of a. Now, this thing is fixed independently of the mesh. And so what this tells us is that if we have, so if the mesh goes to 0, we have that the upper sum minus the lower sum also goes to 0 by this inequality that we have. We said this is less than or equal to the mesh times just a fixed difference, the endpoints, f of b minus f of a. That thing doesn't change as we take this limit. So this tells us the upper sum minus the lower sum goes to 0. So thus, by Darboux's criterion, we have that our function is Riemann integrable. Now, remember, this is in the case that f is an increasing function. So what about if f is decreasing? So now, if f is decreasing, then minus f, so if I multiply f by a -1, this thing is increasing. And so from above, we know that negative f is Riemann integrable. But since the space R of AB is a vector space, we can take any vector, quote unquote, any function in that space and multiply by -1, and you still stay in the space. We have that f, which is equal to negative f, must also be Riemann integrable. And this completes the proof. That tells us everything we need to know, right? So the idea here is we prove the theorem for an increasing function. And then we say, okay, if it's decreasing, then if you multiply that decreasing function by -1, it becomes increasing. I already proved it for increasing functions. I know that the space of Riemann integrable functions is a vector space, so I can multiply any vector in there, any function in that space, by a -1, and it still remains in the space. That's how this works. Okay, so let's take a look at an example. Let f of x equal to 1 if a is less than or equal to x, which is less than or equal to a plus b over 2. So halfway up the interval, this thing's equal to 1. And let's say it's equal to 2 if you're on the other half of the interval. Okay, so if we just offer up a very, very quick, easy sketch of this thing, right? This is a very easy function to sketch out. It's equal to 1 up to some point, and then 2 beyond that. So we have this open circle at the top. We've got a nice jump discontinuity here. And let's say this is b, this is a on the left, and this is a plus b over 2. Sorry, I had to squeeze that in. But this function right here, well, f of x is monotone because it's increasing, which implies f is a Riemann integrable function on this interval AB. But clearly, f is not a continuous function. So what that shows us is that if you are a continuous function, you have to be Riemann integrable. But if you're Riemann integrable, you don't have to be continuous. There are discontinuous functions that are still Riemann integrable. And I gave you one explicitly, right? I built one for you that this thing is Riemann integrable using this theorem that we just proved, but this thing is not a continuous function. So what this really tells us, if we draw out some circles here, if we say, here's one circle, and around it is another one, this tells us that the space of Riemann integrable functions is strictly larger than the space of continuous functions on some interval, right? So every continuous function is contained in the Riemann integrable functions, but it cannot be everything. There is much more that is Riemann integrable. Okay, so let's finish this lecture off with one more proof. It's a variant of the Darboux integrability condition. So it's a slightly easier way to prove integrability. And in this case, it requires you just to find one single partition that makes the upper and lower sums close enough. Now, close enough is always going to be measured in terms of some small positive number, say epsilon. So let me show you what I mean. Let f be bounded on AB. We need boundedness, just like we did for the Darboux integrability condition. We've seen that if you're not bounded, you're not a Riemann integrable function. We already proved that. So boundedness is necessary here. And then if for all epsilon greater than 0, there exists a partition. So it's not for all partitions. Sorry, I spelled that wrong. There exists a partition, which we'll call P0 of AB, such that, well, the upper sum using this partition minus the lower sum using this partition is less than epsilon, then your Riemann or your function is Riemann integrable. Okay, so look at what this says. It says that if I pick a really, really small number, whatever it happens to be, as long as it's positive, 10 to the minus 100, that could be my epsilon. Well, then if you can find me a partition that puts the upper sum and the lower sum within epsilon of each other, then this thing is going to be Riemann integrable. So this is the real advent of this, right? Darbo's condition got rid of evaluation points, but it says that you have to do this in terms of a limit of the partitions. In this case, now you get to choose the partition to make it work. You don't have to make it work for every partition, just need to find one. This is much more in line with what you would have done in a calculus class, where you use something like the left Riemann sums or the right Riemann sums, and you just show that those things converge in, and then you get, say, the abstract or the signed area underneath the curve. The much nicer and easier way of applying the integrability conditions and showing that a function is in fact Riemann integrable. Okay, let's take a look at the proof here. So first of all, let's let capital M equal to the sup norm of F, which we know has to exist because F is bounded. Now, also what we're going to have to do is let epsilon be positive. So we need to start with an epsilon. And by hypothesis, so by assumption here, there exists a partition P0 n is equal to B, such that I can put the upper and lower sums within epsilon of each other. And remember, I'm not putting any absolute values over the upper and lower sums because we always know the upper sum is bigger than the lower sum, right? So I don't need to tack any absolute values around this thing. And pardon me, I'm going to make this epsilon over 2 just so that it comes out a little nicer. We'll see where this comes from in a moment. Okay, what I'm going to do is I'm going to say let delta equal to epsilon over 12m times n. Now, n is the number of elements in my partition. M is my supremum or my sup norm of my function because it's bounded. And in this case, 12, we're going to see where this comes from. So there's going to be a lot of triangle inequalities that are going to come through here, okay? Okay, so we're going to, so we wish to show, maybe it's nice to tell the reader what it is that we want to show. We wish to show that the upper sum of Fp minus L of Fp is less than epsilon when your partition is less than delta. Okay, that's what we want to show, because so that by the Darboux condition, integrability condition, this implies F is Riemann integrable. Okay, so it's important sometimes when we do proofs, we like to write down exactly what it is that we want to do so that we can, have an objective for us right there on the page. Okay, let me start fresh with a nice new piece of paper here. So let's let P be a partition so that the mesh is smaller than delta. And set, I'm going to call P prime equal to P union with P0. Remember, P0 was the partition that I got from my original assumption, from my hypothesis based in this theorem. And then we have, well, because P prime contains P0, we must have that the upper sum using P prime minus the lower sum using P prime is less than epsilon over 2. And this is because we know that this works for P0 and P prime contains P0. Now, here's what we want to do. We want to be able to bound the upper and lower sums between, or sorry, the upper sums between P and P prime. So now note, if I take the upper sum of F using P, and I subtract out the upper sum of F using P prime, I'd like to know how far away these two things can get from each other. So we want to know what these two things are bounded by. Now, remember, P prime contains P. So that means that there's at most little n subintervals from P and at most 2n intervals from P prime that are not common in these upper sums. Okay, so maybe it'll help if you draw a picture in the margins here. But what you can say here is that there is m times n times delta. Delta is the length of each of the meshes. M is the maximal value of the function on each subinterval, right? That is, if we go back, that's our sup norm here. And there are at most n subintervals from P that are not represented in both of these upper sums. That's because P is contained in P prime. Delta is the length of the mesh. Similarly, from the P prime upper sum, there is at most 2n intervals. So I have 2m times n delta. Same principle is at work here. There are 2n intervals. The maximal value in absolute value of each function of the function on each interval is m, and the mesh is delta. So this becomes 3m delta, mn delta, which by my choice of delta is less than epsilon over 4. Why? If we go back and look here, delta is equal to epsilon over 12m times n. So the m times n cancel, the 3 over 12 becomes 1 over 4, and I get an epsilon. Similarly, you can do the same game with the lower sums, and you just repeat that argument, and you can say that this is also less than epsilon over 4 by the same argument. So I skipped a little step going from here to here, and I want you to try and fill in the gap, right? So try and draw a little picture, maybe, if that's what it takes to show the discretization here. If it's easiest for you, try and think about P and P prime differing by just 1 point, right? That's probably a good way to start this out, and try and think through this. But now that I know that these upper sums and these lower sums differ by only epsilon over 4, putting this all together gives, so putting this all together gives, well, remember what we wanted? We wanted the upper sum with P minus the lower sum with P. We wanted to show that this thing is less than epsilon from the we want to show written with the star here. Well, we can add and subtract in the upper sum with P prime. So I've got a nice big triangle inequality coming here. There's an upper sum with P prime plus, now I have to have 2 upper sums with P prime. I'm subtracting it first and then I'm adding it in. I'm going to do the same thing with the lower sum with P prime. And then I'm going to add back in the lower sum with P prime, and I'm left with just the lower sum with P, right? So it's a double triangle inequality application, adding and subtracting those upper and lower sums with P prime. So an old trick. But now, what do I know? I know, so if I just draw an asterisk here, that is this piece right here. Similarly, this piece with the lower sums, that's the last piece of my inequality. And this one right here is coming from this piece right here because P prime contains P0. And so putting all of this together gives me epsilon over 4 from the green asterisk, the upper sums, plus epsilon over 2 from the upper sum with p prime minus the lower sum with p prime, plus epsilon over 4 coming from those two lower sums, which is equal to epsilon as desired. Therefore, my function is Riemann integrable by the Darboux condition based on the we wish to show component here. Remember, we want to show using the Darboux integrability condition that the upper and the lower sums are within epsilon of each other when your mesh is small enough. Okay, so that proof is a little technical. It's a little bit involved, and I glanced over some of the details, which I highly recommend you try and work out on your own. But the advent of that theorem is that it makes applying the Darboux integrability condition much easier for us, right? Take a look at the difference between applying the definition of Riemann integrability using, arbitrary partitions, arbitrary evaluation points. That's quite difficult. Then we made it slightly easier using the Darboux integrability condition, gets rid of evaluation points. Now, this last theorem that we gave here allows us to sort of get rid of arbitrary partitions as well, right? It says, as long as I choose an epsilon for you, you just have to find a mesh that's going to make this small enough. The upper and the lower sum have to be close enough to each other. Doesn't have to work for every partition. You get to choose the partition. That's what makes this much simpler. So we've sort of whittled ourselves down and got ourselves down to investigating integrability with this simplified Darboux integrability condition.